Okay, so welcome to the final seminar of the year in the series. And so we're very lucky to have Nigel Goldenfeld giving this talk. Nigel is a Chancellor's Distinguished Professor in Physics at UC San Diego, and he has done many things in different areas of physics, and he's had lots of awards, and in particular, he's a fellow of the American Physical Society, fellow of the American Academy of Arts and Sciences, a fellow of the Royal Society, and a member of the U.S. National Academy of Sciences. So these are all extremely prestigious. So we're very lucky. Yes, I said that, yeah. But it's worth saying twice. So okay, please take it away. Thanks very much.
You should wait till you hear the talk before you applaud. Okay, before I begin, I'd like to make some thanks. So I'd like to thank Chan Lee, my student and collaborator on this work. I'd also like to thank Terry Samelsky, in whose wonderful neuro AI class I first learnt about double descent, and that I don't want to see this ever again. And I still remember the moment when one of the students was presenting the seminar paper, showed up a picture from one of probably Misha's papers on double descent, and I yelled out, it's got to be a phase transition, and that turned out to be right. I also want to thank Misha for many discussions about the topic, particularly about how to present it to people who are not physicists. And so I've tried to take into account all of those things. All right, so in 1972, Phil Anderson, the Nobel Prize-winning condensed matter physicist, wrote a hugely influential paper in Science magazine. It was called More is Different. And what he was trying to say was that if I have systems that are, the more the number of particles there are, the more complex they are, then they exhibit new emergent phenomena. And he tried to explain, give a sort of forward-looking essay on how that would arise and the consequences of symmetry breaking, and even to issues as philosophical as the hierarchical structure of science. A very influential paper, which really, in some sense, is one of the articles that marks the start of the transition from solid-state physics to condensed matter physics, a much more all-embracing field of science, where the interactions between systems, the emergent and collective properties, are brought to the fore. So I want to start off by just telling you a preview of the results, and I'm going to do this really quick, and then I'm going to go back and tell you in more detail. So let me just tell you about what double descent is. So here you are looking at the error, generalization error, test error, and the training error, and the capacity of a network. The capacity means the model's ability to fit a wide variety of functions or patterns in data. In other words, for the purposes of this talk, you can think of capacity as being the number of parameters in the model divided by the number of data. So let's imagine we have the following question. We have a time series, and we have some data points, and we want to know, can we fit that? So what you might do is you might say, well, it's roughly a straight line, so you make a linear fit like that, and that fit has, it does okay-ish, but it has a lot of error because it really doesn't have enough richness to capture the data. So then you say, well, that was really silly. Why don't we just use a 500th order polynomial, and that way we can capture the data. So there you go. You fit every single data point, but now what you've done is you've fitted the noise. And so if you look at how well this simple model fits the data, it fits it reasonably well. If you look at how this model fits the data, it will fit it exactly by construction. If I look at the ability to generalize, it's going to be pretty poor for this thing because it doesn't really capture all the information in the data. And if you look at this thing, it's going to be contaminated by noise. So then you might say, okay, well, that's fine. So maybe what we should do is have a balance between the bias and the variance, and that would say that you should be operating at this sweet spot over here. So underfitting is too simple to capture training data complexities. Overfitting is a good fit to noisy training data, so you'll get high test error. So it's natural to think that the operating point of neural networks will be at that sweet spot. But the big surprise is it's not. The big surprise is that we are over here, far away from that sweet spot. And in fact, this behavior here marks a change in behavior. Modern neural networks are in this range. This is the sort of classical regime. And this sweet spot, not the sweet spot, this point here is called the interpolation threshold. And that marks the transition between over-parameterized and under-parameterized models. So there's two mysteries here. One is, how do we understand the fact that the test error, the generalization error goes up and then it appears to come down again as we go through this interpolation threshold? And the answer to that is that this is actually a phase transition. And what that means, I'm going to explain in quite a lot of detail in the talk. So that's the first mystery. The second mystery is, well, why do modern neural networks exhibit benign overfitting in the overparameterized regime? And benign overfitting means that as you increase the capacity, actually the error is a decreasing function of the capacity of the network in contrast to your natural intuition. And the answer is, I'm going to show you this is actually a new phase of matter. Of the variables in the neural network. It has emergent properties and rigidity, and those give rise to the good generalization performance. Now, you might say, well, this is obviously preposterous, because why is double descent like a phase transition? So here's a phase transition. You might say a magnet will have the following behavior. At very high temperatures, it will not be magnetic, but as you go below the Curie temperature, the magnetization, which I'll talk about that in a little bit, magnetization increases from 0 and goes to all the spins essentially pointing up at low temperatures. And you can look at this curve and you can say, well, this has nothing to do with double descent. This does not look like double descent. Okay, so that's true. But if you look at the static susceptibility, that measures how strongly a system at equilibrium responds to a constant external field. And that looks like this. The curve shown here, and this does indeed look like double descent, as you can see here. Here's the blowing up that region around the interpolation threshold, looks exactly like what is happening here with the susceptibility. So here's what you're going to learn in this talk, hopefully, or at least learn at some level. First of all, I'm going to explain to you that this is a phase transition, and the response functions that go along with that phase transition are similar to the London equations for the superconducting transition. I'm going to show you that the critical exponents and universal scaling functions, etc., can be computed for the setting of linear regression, and I'll show you that. I'm going to go light on the details, but I'm going to show you the evidence for that. I'm going to show you that in the underparameterized phase of the system, the machine learning algorithm, stochastic gradient descent, obeys the fluctuation-dissipation theorem, and you get an equilibrium that is defined by a Gibbs state. But in the overparameterized phase, the fluctuation-dissipation theorem is broken. You get a non-equilibrium state with broken ergodicity, and the degree of broken ergodicity increases further into the overparameterized phase, and that is the thing that is the origin of the good generalization. I'll explain to you a physical interpretation in terms of this mathematical connection. And I will explain to you, I'll highlight for you as I go along what is new in this. In other words, what are you getting out of this analysis that wasn't obtained earlier by other people? And what you're going to see is that what we're doing here is we're actually going to look at the time-dependent dynamics of training using methods from statistical physics. And in the past, what people did was look very sensibly for equilibrium solutions directly, looking for least norm solutions, but in doing so, missed the emergent dynamical behavior and the broken ergodicity. So I'm going to talk about emergence very briefly. I'm going to talk about emergence in physics, talk about double descent, show you about the analytical dynamical mean field theory, show you about the phase transition and the scaling laws, explain the generalized rigidity, and I'm not going to talk about future work. Okay, so just very quickly, so we're all on the same page. So large language models are believed to have impressive emergent phenomena, emergent, unexpected, unpredictable abilities, as shown in these sort of news articles. Here are some data from that. This is from Wei et al. Looking at emergence of in-context learning in large language models, showing you here a number of examples of different tasks, showing you that as you scale up the model, the behavior undergoes a dramatic change in its ability to perform. This, of course, it looks nice. It is controversial because this may also be a mirage from the way that you measure these things. So this is a topic of debate in the community. But what I'm going to show you is an unequivocal example of emergence in large language models. And so I'm going to show you how we describe and predict and observe the empirical consequences of emergence in physics. So very, very quickly, I want to just go through some of the basic ideas from statistical physics, so that when I then apply them to machine learning, you'll be able to see what I'm really talking about. So let's talk about the most simple example of this. And the most simple example would be the emergence of the solid state from a fluid state. So you have a bunch of particles bouncing around in a box, and as you lower the temperatures, what will happen? Well, they're going to form a solid, and if they form a solid, then that solid state has its own new laws of physics. So here I've drawn the sort of textbook picture of what a solid looks like. You've got a bunch of atoms here in a crystalline array with springs that connect them. Those springs are new long-range forces that are completely distinct from the original forces between the atoms, and we have a name for those forces. The name for those forces is elasticity. In other words, something becomes a solid, it has elastic phenomena. If it's a liquid, it doesn't have that. And the origin of these new laws is the collective statistical behavior of the atoms. And the point about these emergent forces is that when you ask the response of a solid to an external disturbance, it's completely different from that of a fluid. Namely, if you have a fluid, you poke your finger into it, nothing will happen. It will just, you feel no resistance. If I have a solid and I push it with my finger, it can actually move and transmit a force. And that's something very different. It's the response of a solid is very different from the response of a liquid. And we're going to see that that's important for understanding what happens in machine learning. So what I've shown you is that emergence always leads to a sort of rigidity, in this case, the rigidity of an elastic material, but you can generalize this notion for any system, and I'm not going to go into how one does that. This generalized rigidity describes the response to perturbations, and in, say, biological contexts such as ecology, you have such phenomena as well, and this is called a resilience. Now, when you have statistical dynamical systems, such as physical systems in statistical mechanics or offline machine learning with stochastic gradient descent, what happens is at very long times they approach an equilibrium state, and they sample all possible states of the system that do not violate rigorous laws, such as, say, the conservation of energy. And this property, this sampling all the possible states of the system, is what is known as ergodicity, meaning wandering around. So ergodicity means that emergent order is not possible, and I'll show you why, because every state that you might have that, say, is emergent with, say, magnetization in this direction is cancelled out by another state which has the magnetization in exactly the opposite direction. So in order to have this sort of emergence that I'm talking about, spontaneous symmetry breaking, this ergodicity must be broken. And here is an example here. So here is a picture of a magnet. It has little spins, little vectors that come from quantum mechanics. Doesn't really matter where they come from. Here the spins are pointing in random directions, and so there is no net order. But if the spins all line up, as they do below this critical temperature, then the spins are aligned and they do not cancel out. And so here is the phase diagram for that. Here is the magnetic moment as a function of temperature. And at high temperatures, the system is ergodic. It is sampling all possible configurations. And so for every configuration here, which has a magnetization that is positive, there's another configuration over here, which has the magnetization negative. And so the end result is everything cancels out and you get no net magnetization. But if I'm below TC, then you see that the system has broken ergodicity and is now ergodic in this region of its phase space. I've sketched schematically over here. And so this is the ergodicity breaking. And of course, it could have broken ergodically to be ergodic only in the negative magnetization region. So there's two possible ways that you could have ergodicity breaking corresponding to two different possible probability distributions of the system. But here's the thing. If you are in equilibrium, at very long times, the system is sort of going around like this, and eventually, you won't be able to say, where did it start? It will have lost the memory of its initial conditions. That's what equilibrium means. But over here, it won't have completely lost the memory of its initial conditions, because you can say at very long times, well, it must have had a net positive magnetization. That must have been what was in the initial conditions. So ergodicity breaking is associated with a memory of the initial conditions. And when you're below TC, the presence of this ordering then means that the spin system exhibits rigidity, meaning response to perturbation. And if it's random, it'll do nothing at all if you try to perturb it. But if you are below TC, where you have a magnetization, the spins are all trying to point up. And if you disturb them, you'll see that they form some kind of oscillation, some kind of spin wave, which is just like the elasticity that you would have in a solid that is turned into a crystal. So there's another thing that happens then. There's another thing that happens when you're very close to the phase transition. If you're very close to the phase transition, you'll find the following phenomena. You take the magnetization, and you might say the magnetization will depend on temperature, as I've shown you, but it may also depend on the external magnetic field. It should be a function of two variables. But if you plot it in a particular way, which I'm not going to go into, then you will find that you scale the temperature in a certain way, you scale the magnetization in a certain way, a way that is predicted by theory, then all the data fall onto one universal curve here. And the way that these data are scaled depends on certain numbers called critical exponents. So those critical exponents apply to all different materials measured. So here I'm showing you data from 5 different magnetic materials. They all have different atoms, but irrespective of that, when you plot the data in the way that theory predicts, then they all fall into one universal curve. The other thing is that the scaling laws, which I'll show you later, the scaling laws are independent of the parameters in your system. They don't depend on the interactions between the spins or the atoms and things like that. They're just pure numbers that you can compute from theory. And we're going to see that also in machine learning. And the other thing I want to point out is, here are these data from real magnetic materials, and you can see here that if you're close to the front, you will see it. There's a solid line which is nearly obscured by the data. That line is the line predicted by theory. There's no adjustable parameters in that line. It fits it without any adjustable parameters from the renormalization group theory. All right, so here's the questions that we're trying to understand. When you have a continuous phase transitions, you observe power laws, and they're understood by renormalization group and statistical field theory. The Nobel Prize in physics was given to the person who really finished our modern understanding of these phenomena. I've shown you about data collapse, and I showed you earlier the spin stiffness in the magnet. Now, in machine learning, as I showed you, when you look at emergent phenomena, the claim is that there are sort of power law scalings, and this idea of scaling machine learning is a very important thing for tech companies, for example. So you might say, well, are there analogs of all of these phenomena as well? And indeed they are. And here I will show you this is the data collapse version for neural networks, and the ability to generalize accurately in context comes from this behavior here. So that's the answer. So now let's get into it in a bit more detail and see how do we really make this connection. So the setting that we're using here is a double descent in linear regression. So here's linear regression in one dimension. You've got some data points, and we try to fit a line through those data points. So that linear regression in one dimension, we're going to do it in d dimensions. So I've got n input data. The data are generated in a space with dimension d. There are some coefficients, the beta I, that connect the line, the label as it's called, to the input data, and then there might be some noise that comes in the data, and so D is the dimension of that. And what we're trying to understand is we have an estimator, which I'll call beta hat, and we're trying to search for the best beta hat by minimizing a loss function, and there's a loss function over here. So that's a very standard setting for machine learning. So now let's have a look at what we did. So we took that problem, and then we did a simulation of this. And here's the data from the simulation. So the black curves, the black dots are the data for the generalization or test error. The blue data are the training error. And you can see the training error go to zero when the capacity becomes 1 in this particular case. And at the same point, you can see that the test error is diverging, and this is the hallmark of the double descent phenomenon. Okay, so that's the simulation. This is the theory for this, and the theory, as you can see, goes right through the data points and predicts everything that we see. And I've got some formulae here, which I will talk about a bit more. But the most important thing is that this quantity here depends on the initial condition, and these other quantities are defined over here. Alpha is the capacity, and D is the variance of the label net. So this is the theory. This is the phenomenon. Now, how did we do the theory, and what are the new predictions and conceptual ideas? So what is our goal here? So what we're trying to do here is we're going to compute the test and training error. We're going to use mean field theory, a form of mean field theory, where we take the limit that the dimensions and the size of the data is going to infinity, but the capacity, the ratio of them, stays constant. This is like a thermodynamic limit for those of you who are statistical physicists. We're going to explain the performance near the interpolation threshold, and then we're going to see the emergence of generalization beyond overfitting in the overparameterized regime. So let me now give you a quick tour of how we do the calculation. And it's not a very easy calculation, even for people who are experienced in statistical mechanics. So I'm only going to give you a flavor for how we do the calculation. So you shouldn't expect that you'll come out of this seminar saying, okay, now I know how to do the calculation, I'm going to do it myself, okay? Don't do this at home, okay? It's like 100 pages of algebra, and it's difficult to do, but you'll get the general idea. So what we're doing here is we're looking at the stochastic gradient descent. So here is our estimator, which is being updated. This is the learning rate. This is the loss function. And we've added here an external perturbation so that we can look at the response of the system later on, and that will be important. What we're doing here is we have these quantities S, which are basically, we're sampling the data with different little batches of data. So we call that's called a mini batch, and we're sampling different sets of the data. So we do different iterations with different samplings, and so that's a form of stochasticity that is coming into the machine learning algorithm, in addition to the stochasticity that is already present in the data itself. And so then what we want to do is we take the small learning rate, as is usually the case, to turn this into a continuous time equation, which is known as a Langevin equation, and is, of course, highly studied in statistical physics. So then here's the part that most of you will not know. The way to take a stochastic partial differential equation, the way we understand it in statistical physics in order to expose the phenomenal phase transitions and so on, is we turn this into what's called a path integral. So it's an infinite dimensional integral in function space. And the way we do it, if you haven't seen this before, you're not going to get it from this talk, but I'll show you the pictures anyway, show you the equations. So what you do is you write down a thing called the partition function, which you can think of as being a generating functional for every possible quantity that you would want to ask about the statistical physics of any physical system, whether it be machine learning, magnets, superconductors, whatever. And since you've got a Langevin equation, you can just write write that down. And the way we do it, the trick is to put the Langevin equation into a delta function. So this delta function being 0 means that the Langevin equation is satisfied. And so we've put in there into this delta function the stochastic gradient descent of dynamics. And then what the trick is that we turn this delta function into an integral by a Fourier transform. So we basically take delta of x is equal to the integral of e to the I kx dx divided by 2 pi. Everybody learned that on their mother's knee. So we're doing that in infinite number of dimensions. And so when you do that, you get a formula that's shown over here. You have a new variable, which is the variable that comes from the delta function. And you have in this exponential, this complicated action, as we call it, that looks something like that. Okay, so that's turned the whole process of trying to be able to compute statistical averages of whatever you're observing in terms of computing a partition function and then generating moments from that. So this partition function is very strongly interacting. And so what you do is it's strongly interacting because you've got data sets that are random and so on. So what we're going to do is we're going to average over the probability distribution of the noise that's in the data, and then we're going to do a mean field approximation to this integral, which basically means, for those of you who know integration, this is like doing the method of steepest descents, but this is method of steepest descents for an infinite dimensional integral. And when you do that, what happens is the learning dynamics factorizes and decouples into independent components. What makes this problem hard is that it factorizes into many different components, and so you get a whole slew of coupled differential equations, which I'm not going to show you. I can show you them if anybody wants to ask me, but you end up doing that, and then from that you can get an effective equation, which ends up being an effective equation for one neuron in your neural network that then interacts with itself in a self-consistent way and represents the behavior of the entire network of interacting neurons. So the bottom line of all of these technical manipulations is you've turned a many-body problem, a many-neuron problem, which is stochastic and interacting, into a problem with one effective neuron that describes the behavior of the system. Now, the thing that we're going to measure are two quantities. One is what I'll call a response function, which measures how any external perturbation at time t2 affects the model state at a time t1. And of course, we expect our system to be causal. So if the time t2 is larger than the time t1, you apply a perturbation before the time you're measuring, you won't see anything at all. But if you do, you can then calculate the response function that tells you how the observable, your estimator, varies with the perturbation at time t2. So that's one quantity that we measure. Another quantity that we measure, and when I say measure, I mean calculate, is the correlation between the deviation between your estimator and the ground truth at two different time steps, and that is shown over here. So those are things that we measure. And those of you who are here from physics and have heard me lecture on statistical physics and emergent states of matter, you'll know that the response and correlations are intimately related, and that's the case here. So what happens then is that this partition function essentially just factorizes into a product of partition functions, and then we can go ahead and read the effective dynamics from the representative Z bar for this one essential degree of freedom. Now, when you do that, in the end, what you end up with is another Langevin equation, and that Langevin equation is for this effective Langevin dynamics for one degree of freedom, and it looks something like this. So let me just walk you through this. So this part here is a term that you can see as your estimator beta hat approaches the ground truth, this is going to get smaller and smaller. So this is sort of like a relaxation time approximation. It's going to gradually relax to the ground truth. But then there is noise that is driving it, some stochastic noise, which comes from the training dynamics. And we can compute exactly how the noise is characterized, and it's a very complicated formula as shown over here. So then what we do, once we have this effective equation, now we can write down the equations of motion for these two key observables, the response function and the correlation function of the system. So when you go ahead and do that, you get equations that are shown over here. And then from these equations, you can then derive a formula for the training error and a formula for the generalization error. So you can relate both of these quantities to these response and correlation properties, and in fact, to something that looks like the susceptibility that I told you about for a magnet. Remember what a magnet was you had spins that ordered. If you applied an external magnetic field, the spins would order more or less in the direction of that applied field, and the susceptibility was the thing that diverged and gave you the double descent behavior. And so what I'll show you is that these training errors and generalization errors are related to the susceptibility of this dynamical system. Okay, so let me show you what we predict here. So here is the error value. In this color, it is the generalization. In this color, it's the training error. And these are for different values of the network capacity. And you can see that after some time, the training error goes to 0, and the generalization error goes to some non-zero value. This point here, this is red, right? Is this correct? Yes, this is red. So this is the special case alpha equals 1, which I'll say something about in a minute. So we take the long time limit of those things, take that number for the error value, and then we plot it over here. And now you've got the error value as a function of alpha for taking the long time limit. And that's how we generated the data that I showed you earlier on in the talk. So that's what we do in the simulation, and we can compute those quantities using theory, and they give you the solid lines shown over there. Now, I want to ask the question, what happens when we are in the vicinity of the critical point? So we're going to understand now and look at double descent through the lens of phase transition theory. So here's what I already showed you. I showed you that when you have a magnet, say in physics, you might say above TC, there's no magnetization. Below TC, there is some non-zero magnetization, and it has ergodicity breaking, is what I told you and tried to convince you is true. And you have the susceptibility shown over here, how the magnetization responds to an external perturbation. And that's the thing that shows you this divergent behavior. So now we can go ahead and calculate that from our theory. And it turns out that this susceptibility is the response function in the limit of omega goes to 0. And this is, as you can see, has a divergent form as alpha tends to 1. So the susceptibility diverges as alpha goes towards 1. And the system is ergodic if we're below the interpolation threshold, and you can compute the susceptibility in that way. So that's what happens. Omega here, I didn't see what omega was, and I should just quickly say that. So we've looked at the dynamics of the system in time, but we're also going to, since we're physicists and we're trying to look at fluctuations about the long time behavior, so then we also look at the Fourier transform variable in time, and that's what omega is. So we're looking at the frequency dependent behavior. So what I've shown you then is that the generalization error for alpha less than 1 turns out it depends on the susceptibility, and it has this form here, and it diverges as we get to the interpolation threshold. Now, when alpha is greater than 1, it turns out that this response function, this frequency-dependent response function, the Fourier variable, which is conjugates to time, we're just doing the Fourier transform in time, that variable exhibits an extra pole, and I'll show you that in full detail in a minute. And this behavior here, as I send omega to 0, this clearly is going to infinity, and something very strange is happening, which I'm going to have to explain to you. But the end result, the physical meaning of this, is that the dynamics of the system is out of equilibrium. And it's out of equilibrium, and I'll show you exactly why, but there's also an ergodicity breaking that has happened. In other words, I'll show you this again, but what's happened in this regime for alpha greater than 1, the parameterized regime is now you've broken ergodicity, and the amount of ergodicity breaking you have increases with how far above alpha equals 1 you are. Alpha equals 1 is the transition. So the greater further you are above that, the more ergodicity breaking there is, and I will show you the formula. So this ergodicity breaking degree, this is this variable alpha minus 1 of alpha, we call that the ergodicity breaking degree, and as I'm going to explain to you, this is a measure of the persistent memory of the initial condition and a persistent memory of the training data. So now when I work out the formula for the generalization error for alpha greater than 1 in the overparameterized regime, now you get the same terms you saw before, but now you get these extra terms here. And remember, this thing here is the initial correlation, and this now depends on the initial conditions, and this is the thing that multiplies the alpha minus 1 over alpha, the degree of ergodicity break. Okay, so now we've got that formula here. So here are the two formulas now for the overparameterized regime and the underparameterized regime. And you can see that there's a divergence on both sides of the transition as you approach from above and below the interpolation threshold. Now, this term here, I wanted to say something about this because this is a very important point. Usually, as I've said before, when you look at the long-time equilibrium behavior, that means that you forget the initial conditions. But this term depends on the initial condition. So this is the thing that you see, which is the hallmark of the ergodicity breaking. So the long-time behavior of the neural network remembers the initial condition in the overparameterized regime. And this is the term that is missed if you just try to construct equilibrium distributions with minimal norm without actually solving for the dynamics of the training process.
So,
yes.
Back to my slide. But that term in red, alpha minus over alpha, goes to 1, right? As alpha goes to infinity. So does that mean perfect memory
yes.
of the initial condition?
Yeah. Yep. Yep. So now let's have a look and see what happens in the vicinity of this this interpolation threshold. So I told you that when you have a phase transition, as we seem to have discovered here, then there are various phenomena that follow from that and predicted by the modern theory of phase transitions. So let's have a look at what theory predicts. Excuse me. So if we look at what we would expect from theory, I'm not going to explain to you, give you a whole course on the normalization group, but what you expect is this. I've got the generalization error. It depends on time, and it depends on alpha, the network capacity. Just like I showed you before, the magnetization of a magnet depends on temperature and external field, depends on 2 variables. So this ostensibly depends on 2 variables, but what happens, in fact, and we expect this to happen, and it does happen, is that it will actually depend on 1 variable, and that 1 variable, the theory will predict to be of this form here. So you look at 1 minus alpha to some exponent phi times gamma t over 2, and this divergence over here. So the theory predicts this, and this f here is the universal scaling function. I think I've got a picture of this here. So remember, in this thing here, there's a solid line that goes through here, which came from theory. So that is the thing that is the f in this formula here. And you can see that what happens is what this predicts is the following. Suppose I go towards the interpolation threshold, so alpha is equal to 1, then this thing is going to infinity here, and this thing here is going to 0. So that looks weird. How can you get something out of that? Well, what has to happen is that this function has to be such that what happens in here outside and what happens in here, they cancel out. And so that requirement says that there has to be a particular form for the scaling function at large times, and you relate this exponent here and this exponent here. So what this theory predicts, in fact, then, is that as you go to the critical threshold, the interpolation threshold, where alpha c is equal to 1, what is going to happen is that the generalization error never converges. It diverges in time, and it diverges on time with an exponent which is gamma over phi, sigma over phi. And when alpha is not equal to 1, then this function goes to a constant, and you get this divergence, as we have seen before. So when we do the calculation that I showed you, what happens is the theory predicts that sigma should be 1 and phi should be equal to 2. And if you do a very complicated calculation, which Chan miraculously performed, you get this very, very complicated form for the scaling function in terms of error functions and exponentials and things like this. And that's the thing that goes straight through the experimental data we get from just doing simulations. These exponents, this gamma, so not gamma, this phi and this sigma, those are just pure numbers. They don't depend on any of the parameters in the machine learning, so they're independent of the hyperparameters in the machine learning. They're universal, just as you get in phase transitions. And in the thermodynamic limit that we're considering here, where you have large training data and network capacity, then we expect on technical grounds that mean field theory will be exact, and indeed it fits very well the data. Now, this data collapse here, let's see if that can happen for machine learning. So here are simulations for the generalization error plotted as a function of alpha and as a function of time. And then if you plot the generalization error in the way that theory predicts, all these data collapse onto this one universal curve. That's true for the underparameterized regime, and in the overparameterized regime, you get the same thing happens. So you get the data collapse in the neural networks, just as you get the data collapse in the physical systems. And this function that goes right through the data, that's not just a curve to guide the eye, that is the mathematical function that was calculated that I showed you before. Okay, so now I've shown you the main results, but let me explain to you something else about this, which is really, really remarkable, which is how to understand this physically. So what I'm going to show you is that this emergent benign overfitting that we've predicted and shown you actually is very much like another phenomenon that we've seen in physics, and that is superconductivity. So I'm going to show you how we make that connection. And even if you don't know what superconductivity is, I'm going to show you a simplified form of superconductivity that will explain the point, even if you haven't seen it before. So first of all, I showed you that we can calculate the response function. We take it calculated in time, then we take the Fourier transform and frequency, and we get these complicated formulae here. All I want you to notice from these formulae is that A, they're complicated, and B, you have to look very carefully at what happens when omega equals 0, because there's a singularities and things here. And to compute the real and imaginary parts, you have to use causality and Kronig relations and so on. All of that is fairly standard. Okay, so that's the form, the exact form of the response function. Now let me tell you about something very simple, and that is a simple model of electrons moving in a metal. And this model goes back probably about 100 years. It's called the Drude theory. So what you do is you write down Newton's equations of motion for an electron in an external electric field, which accelerates it, but the electron also can get scattered by bumping into atoms and other things that are in the crystal. And so the equation of motion that you would write down is you'd say Newton's equation is F equals ma. A is the acceleration, which is dv by dt. So mdv by dt is the force, but that's the electric field force that accelerates an electron. And then the electrons get scattered by impurities and atoms and so on. And so what we say is that, well, there's a term here which then causes V to go down, and there's some relaxation time which describes the sort of mean time between the collisions of the electron with its with the other materials. So you take this equation, take its Fourier transform, and solve it, and you get an equation for V as a function of omega, which looks something like that. And that's the simple Drude theory of a metal. And so if I look at this if I look at what this means, so here's what it means. I know the velocity as a function of frequency when I apply an oscillating electric field to a system. Okay, Who cares? Okay. Well, there's a thing called Ohm's law, which you all learned on your mother's knee when you were taking apart radios and building fuzz boxes for your guitar and things like this, when you spent 10 years in your parents' basement being a geek. Okay, or at least that's what I think. All right. So Ohm's law says that voltage is current times resistance, which means current is voltage divided by the resistance. And then the way that we write this for our graduate students or advanced undergraduates, just to confuse them, is we write it down in terms of current density. So the current density is related to the velocity of charged carriers with density n moving past a point in space. And that's related to the conductivity, which is 1 over the resistance, times the force that's being applied. So that's Ohm's law in frequency space. And I just showed you that for normal metal, you can calculate that in the relaxation time approximation, let's say. Okay, so that's just a normal metal. Now what happens if you have a superconductor? So in a superconductor, what happens is that you see that this the relaxation time goes to infinity. There is the time between scattering events goes to infinity. And so then this tau will go to infinity. And so what will end up happening is that you will get just some tau to infinity, you'll just get n e squared over n, some constants, divided by 1 over I omega. But that's only true if omega is not equal to 0. If omega is equal to 0, there's another part that comes from that, which is this delta function here. So the point is that you have this singularity as 1 over I omega in the conductivity. And conductivity, as you can see here, is the response of the system to a perturbation, the perturbation being the applied electric field. So here is what I derived for you just now for electrons in a material. Here is what I showed you comes out of the calculation for the response function of a neural network. And you can see that we get this term here, which looks like this term here, and these terms here, this term here has this extra pole that has this 1 over I omega. There isn't an I omega in this one, it cancels out because of the way what happens when alpha is less than 1. If alpha greater than 1, there is a pole like that. Now, what is the consequence of this pole here? The consequence is that you have a persistent current. And the reason is this. Take a Fourier transform. So I've showed you that the conductivity goes like 1 over I omega, and that conductivity comes into this equation here. Take its Fourier transform. So then the I omega j goes like that, and then I omega is the same thing as d by dt. So this says that dj by dt is equal to E of t. So that's what this equation tells you. In a superconductor, Ohm's law breaks down. You have an equation that looks like this. And why this is important is that if I set the external field equal to 0, what that means, I can integrate this equation, and it says that the current at time t is just the same thing as the initial current. It has remembered its initial state. And if I create a current in a superconductor, it will last forever because of this equation. So that's the persistent current. So that's the simple derivation of superconductivity. So the significance of this pole here is this persistent current that never dies out. What's happening in the neural network case is that you have a persistent memory that never dies out, and that is the ability to generalize. And furthermore, that ability increases with the degree of ergodicity gradient. So let's write down the same equation now for a neural network. So we have the equations for the deviation from the ground truth. So we write it down like this. This was an external force. This is the equation that those formally predict. And then take this, turns into the time domain. You get this formula here. And then, so this is now d by dt of the deviation goes like alpha minus 1 over alpha times the external perturbation. And if I take the external perturbation equal to 0, that means that the deviation has a persistent memory of the training, and that is the analog of the persistent current in a superconductor. So what I've shown you then is that in physical systems, you have all of these phenomena at a phase transition. You get the same phenomena in machine learning, the data collapse, the scaling laws, and the analog of the spin stiffness was the neural network's ability to generalize accurately in context. So here's a slide which I don't expect you to remember, but it tells you about the full detailed description of how this analogy, this mathematical analogy works out. The main thing is that the analog of the number of superconducting electrons is the degree of ergodicity breaking, this parameter alpha minus 1 over alpha. Now, here's something that's very interesting. If I have a superconductor, as I go below the critical temperature of the superconductor, its ability to superconduct gets better. You still have a supercurrent that will last forever, but now the magnitude of that supercurrent increases because more and more electrons are participating in the supercurrent and less are participating in the scattering processes. And the same thing happens in machine learning, that you get more and more neurons as you go through the overparameterized regime, go above the interpolation threshold, more and more neurons are participating in the persistent memory of the training. So now I'm going to show you what that means. So now I want to talk about ergodicity breaking and explain to you why it enables good generalization. I'm going to do that by a very sort of whimsical example. It's not an example that I've calculated. It's like, assuming this is all true, now let's apply it to a very, a context that everybody would like, which is a large language model, and just see what it might mean, just to give you some cartoon picture feel of what is going on. So in superconducting transition, what's called the helicity modulus, the number of superconducting electrons, the fraction of electrons that become superconducting, increases as you reduce the temperature below the critical temperature. The ergodicity breaking degree, that increases as you go through the interpolation threshold, and so the dynamics remembers the initial condition more. And now I'm going to show you what that means. So let's suppose we have a fanciful example. So this is just a sort of cartoon picture, just to give you intuition. Suppose you're taking a network and say, well, what is the weather like in San Diego? If the system is completely ergodic, it's going to just have, sample all the phase space, it won't know where it is. And so it might say, oh, well, I think you should go to Paris. That would be, it's good that it can talk, but it's like completely useless. I hadn't answered the prompt. On the other hand, let's suppose you've got some degree of ergodicity breaking. So now, in this particular case, we're saying as a fanciful example, well, the weather is pretty sunny in New York. Well, okay, it's not bad. It's talked about weather, hasn't quite got San Diego, it's got New York, but it's broken down. It's no longer completely random as it is when it's ergodic. It's now at least focus something on the prompt that you're talking about. Now let's suppose that we increase the ergodicity breaking even more. So now you can imagine that the system is ergodic, and you're looking at in this region here, and this is where you're looking. You're asking the question, what is the weather like in San Diego? And maybe this time you'll say, well, the weather is pretty sunny in San Diego. It's 70 degrees. Okay, so the degree of ergodicity breaking corresponds to the degree of specificity of the performance of the network in response to a perturbation, which is what generalization error is. So in a sense, the function class is reachable within the small neighborhood of the initialization, is able to interpolate the data, but there's only some small subset of soft directions in the parameter space contribute to the effect of generalization. And that's the neurons that are contributing to the generalization ability. In the usual picture of double descent, the geometrical picture, this corresponds to saying, well, you do some singular value decomposition, and you have a whole bunch of eigenvectors that correspond to just the noise, and then you have a small number that are related to the signal, and that's the sort of standard picture of double descent. And so this picture here is not orthogonal to that at all. It's a different understanding of what that means. Okay, so I want to end now by talking about another thing. Okay, is this completely unprecedented? Oh gosh, so let's go away. So is this completely unprecedented? Well, it's not. So here is John Hopfield's paper from 1982 in PNAS. In fact, Tony and I are writing a perspective about this famous paper, the one that won the Nobel Prize in physics. You can see it talks about Its title is Neural Networks and Physical Systems with Emergent Collective Computational Abilities. And the question he's sort of asking here, this is now a few years, 10 years after Anderson's More is Different paper, he's asking, do analogous collective phenomena, analogous to the ones that happen in condensed matter physics, in simple interacting neurons, have useful computational correlates? For example, are the stability of memories, the construction of categories of generalization, or time sequential memory, emergent properties and collective in origin? That's the question he was asking at the time. And if you go and look further on in the paper, there's one mention of the word ergodic in the paper. So here you are, he realizes that as he's doing his numerical experiments, that his systems broke ergodicity. They didn't wander ergodically throughout state space and sample all the points. They actually settled into limiting behaviors, such as a stable state, and a few stable states were the basin of attraction of the flow from most of the initial state space. And he gave some examples and documented that. And later in the paper, he talks about how the phase space flow is dominated by attractors, which are nominally assigned in memories, each of which dominates a substantial region around it. And the flow is not entirely deterministic, and the system responds to an ambiguous starting state by a statistical choice between the memory states it most resembles. This is the ability of an associative memory to be able to reconstruct the data, even if given a partial prompt. So you can see here that the work that we've done in the context of machine learning in modern machine networks in with a vastly over-parameterized regime, these same questions were also on Hopfield's mind 40 years ago during these early days of neural networks from this fundamental perspective of statistical mechanics. So what are the things that we're thinking about? We want to, of course, develop a renormalization group interpretation of double descent. And why do we want to do that? Well, because if we have a renormalization group version of our dynamic mean field theory, then we can understand questions, for example, such as what is the universality across architectures? In physics, the universality classes are determined by very well understood parameters. And so you might want to ask, well, is a transformer in the same network as a perceptron or something like this? Well, all of those sorts of questions one can ask, and one can even find models which are maybe better architectures that still reproduce the behavior as well as, say, transformers or whatever is the favorite architecture. So we also want to understand how the details of what we've just done for a simple network, how it applies to other systems. We want to understand task-dependent emergent behavior. And one thing I'm not going to talk about, but which is a very obvious consequence of this dynamical model of the learning process, is that we can start to understand in a very quantitative way the phenomenon of grokking, and that's something that we are already working on. So here is my summary. I've shown you that we can understand the test error divergence, the interpolation threshold. We understand all of the scaling laws and the details of that. We understand why you get the benign overfitting in the over-parameterized regime. There's other things I haven't shown you, such as what happens when you do regularization and things like that. That's all worked out in our paper. So I'll end by just saying, yes, indeed, more is different. More is different, even for neural networks. Thank you very much.